Okay, let me get this first, just for recording. So that's the how we derive the formula of sector area, and then apply this into the area of region in polar coordinate system. Okay. Oh, by the way, I think earlier I forgot to mention about the little approximation. This thing here. You see that the sector that I approximate that is actually not exactly the same to the region marked by yellow color. However, notice that the efficiency I have here is actually being compensated with the surplus I have here. Do you notice that? Okay, so if I kind of like, let me super enlarge that a little bit. Okay, if I super enlarge that, so let's say this is the sector, okay, and the following is the curve. Okay, the following is the curve. Now notice that the extra that we have here somehow being compensated by the deficit that we have here. Of course, not perfect though, not perfect. But you will see this kind of like error will get a lot smaller. It will get a lot smaller when this becomes d theta, when this becomes very, very small. Okay, now that's how then we get that formula. Now, applying that to number 4, this is what we get. And then for number 6, this is what I get. Okay, now for number 6, continue from this number 6, then the angles will be from 0 to pi. Okay, and then let's see how to compute that. Again, I assume you should be able to compute it on your own. Okay, now you will see, let me split it further. This is 1/2 pi for the first term. The first term, later on this becomes this. Okay, and then for the second term, this guy here, you will see that becomes, believe it or not, okay, I'll write it down first. This is integral from 0 to pi of cosine theta d theta. Okay, and then the last one, there will be plus integral from 0 to pi of, let me make a double angle right away, 1 plus cosine 2 theta over 2 d theta. Now what I want to say is the following, that that this guy here later on will be 0. Okay, how can you do it so fast, Thomas? Well, because I happen to know that the graph of cosine theta looks like this in quadrant 1 and quadrant 2. Okay, where the area here is opposite of the area here, right? So they're supposed to kill each other. Okay, in fact, furthermore, the same thing can be said about this part. Okay, because from 0 to pi, the period is pi though. So from 0 to pi, this is pi here. Now the area here, it's the same to the total area here. Okay, so then if I go on with computation, I will get 1/2 pi plus another 1/2 pi. That's equals to pi. I think I forget the 1/2. My bad. I forget the 1/2. So I should put 1/2 here, another 1/2 here. So this should be 1/4. So it's 3 pi over 4. Okay. Now, what's the difference between question number 4 and number 6? Not much difference, except that in number 6, they don't tell us the limit of the integrations. We need to find it ourselves. Okay. Now let's apply that idea to number 8. Number 8, we have r equals to, the equation is r equals to sine 2 theta. Good news, they give us the graph. It looks like this, and then later on continue here. Later on continue here. Later on continue here. Okay, what we need to find is the area here. The area of one leaf. Okay, so the area will be, the area of that one leaf will be 1/2 integral sine squared 2 theta d theta. Okay, again, I hope you realize that the issue is with the limit of integration. Okay, now how to find the limit of integration? Then I need to find when I start from here, when I start from origin, go back to origin the first time. What are the angles? Now you can see when theta equals to 0, the radius is 0. So that one is fine, right? Okay, when is the next time the radius gets to 0? Okay, that's the issue. When is the next time the radius equals to 0? Okay, let's solve it then. I set the equation to be equals to 0 because I want to see the radius equals to 0. But from trigonometry, we learn sine 2 theta equals to 0 when 2 theta equals to, and 2 theta equals to n pi. Right? So theta equals to n over 2 pi. Okay, so when n equals to 0, the theta is 0 as we expected earlier. And the next time it comes back to origin is when theta equals to 1. That's pi over 2. Okay, now then I can update my limits of integration now becomes area equals to 1/2 integral from 0 to pi over 2 of sine squared 2 theta d theta. Okay, now how to integrate that further? And I do double angle formula. It's 1 minus cosine 4 theta over 2 d theta. Okay, now notice that the first term will give us 1/4 of pi over 2 minus the second term, when you integrate that, will give us 1/4 times 0. Oh, how do you get that 0, Thomas? Well, because I know the following. Cosine 4 theta makes one cycle, one period in pi over 2. So you see how I play the game? Okay, instead of computing it, look at the picture. Okay, so you see that the area here, let's say is x, and this is x, but this is negative 2x. Okay? Then from there we see, oh, then the area of that one leaf is pi over 8. Now, the purpose of me doing number 8 is actually not to teach you the integral, but to focus more into how to find the limits of integrations. Okay? Now, but before I go even further, I need you to realize a couple of things about this number 8. Let me bring your attention to my graphing software. What we had earlier was sine 2 theta. That's what it looks like. Okay. Now, sine 2 theta, that function is depending on sine of theta. Okay. Therefore, it must be symmetric with respect to the y-axis. Okay. And you also notice that sine 2 theta can be rewritten in terms of cosine. Therefore, it is symmetric with respect to x-axis too. Now, what I want to show you is the following. Do the comparison between sine 2 theta and sine 4 theta. Sine 2 theta has 4 leaves. Sine 4 theta has 8 leaves. Sine 6 theta will have 12 leaves. In fact, the same pattern applies when we have cosine. The difference is for cosine, it starts from the maximum. When it is sine, it starts from origin. Okay, but the number of leaves equals to the coefficient of the angle multiplied by 2 if the coefficient is even. If the coefficient is even. So let's go back here. I make it cosine 4 theta. You will see 8 leaves. If I want to make 24 leaves, then cosine 12 theta. You will see 24 leaves. Okay. However, if the coefficient is odd, let's say 3 theta, then the number of leaves also odd. Okay. If the coefficient is odd, then the number of leaves also odd. The same number. Cosine 5 theta will give us 5 leaves. Cosine 7 theta will give us 7 leaves. Okay, now, so let's take a look. If we go back to our notes, let's write it down. The following situation. Okay, node R equals to sine theta, or R equals to, sine n theta. N theta or cosine, R equals to cosine n theta will have n leaves if n equals odd. It will have 2n leaves if n equals to even. Okay, so if you think about it, when it is even, you have to double it, right? Such that under no situation, actually, if you think about it, under no situation, any one of these will give you 6 leaves. it will not give you 6 leaves. Okay, so the number of leaves will be either a multiple of 4 or an odd number. Okay, now that's not something we don't need to remember though. That's something we don't need to remember. Just kind of like, hey, you know what? It's something nice to know quite fast. Now, how about the radius? The radius, we can put a constant here. Let me put A here. Then it will basically enlarge the radius of the process, if you want to call that process. Let me go back. Notice that this is roses or flowers with radius 1. Okay, now putting a number in front of that, let's say I put insert 2 here, it will make the rows being stretched by radius 2. Okay, let's do comparison. Let's do comparison. Use cosine 3 theta. And then I compare that with if the radius is 1. You see? Okay. So basically what happened is you stretch the red flower, the red rose, to the purple one by radius 2, by a factor of 2 away from the origin. Okay? Now, I hope, if you have hard time to memorize that, watch this lecture video again. As you know, I usually post this lecture video on my YouTube channel. Now, let's go back to our problems. Okay, let's say, for example, question number 12. Question number 12. Sketch the curve and find the area that it encloses. Sketch the curve. So R equals to 4 plus 3 sine theta. It depends on sine. So it must be symmetric with respect to y-axis. Okay, that's one. Second, because it follows, that's one. And then second, because it follows R equals to A plus B sine theta, then it must be the type of limation. Okay. It will look like approximately like this. Okay, when theta equals to 0, that's 4. When theta equals to pi over 2, that's 7. When theta equals to pi, that's 4. When theta equals to 3 pi over 2, that's 1. So the curve approximately looks like this. Like that, approximately. Okay, and then later on, I will copy paste that here, approximately. Now, then what is the area of the region? Now, I will do the following. The area of this, the total region, is twice the area of this yellow one. Why? Because of the symmetry. Okay, so the area there and the area here should be the same. Okay, now then the area equals to 2 times area on on the left hand side, but we know that this guy here is when theta equals to negative pi over 2, and this is when theta equals to pi over 2. Okay, so that would be 2 times 1/2 times negative pi over 2 to pi over 2 of 4 plus 3 sine theta being squared, which will be integral, the 2 and 1/2 cancel, from negative pi over 2 to pi over 2 of 16 plus 24 sine theta plus 9 sine squared theta d theta. Now you will see, I hope you see that right away, that this gives you 0. Okay, why? Because sine is an odd function. Okay, sine is an odd function, and the domain of the integration is symmetric around x equals to 0. Okay, and this will be 16 pi for the first term. The second term will be 0. The last term, let me slow down a little bit. That's integral from negative pi over 2 to pi over 2. I pull the 9 out, I do double angle. D theta. Okay. And again, you will see that this part gives you 0. For the same reason. Okay, for the same reason. Then I will get, hold on, I need to do this first. And then I will get 16 pi plus 9 over 2 times pi. Okay, 9, this 9 here, 9 over 2 multiplied by the length of the interval, which is pi. Okay, so that will be 32, 41 pi over 2. Now that's for number 12. Let me do one more. Number 18, for example. You will see the issue is not about how to set up the integral. I mean, we know how to set up the integral, but our issue is more about, hey, how do we know, for example, how many loops it has, right? And what are the limit of the integral? Suppose number 18. I picked this question because I don't know what it looks like. I don't know what it looks like. But the question is, find the area of the region enclosed by one loop of the curve. By one loop of the curve. Now, if it makes one loop, then the loop must go from origin to origin, right? Okay, which means we need to find, quote unquote, instead of the x-intercept, okay, instead of the x-intercept, you can call that the theta intercept. Okay, basically when the radius equals to 0. So 0 equals to sine to theta. Okay, honestly, I don't know what it looks like though, but I think it should look like this. I think it should look like this. I think it should look like that because of the r square. Yeah, because of the r square. Okay, if this were r, it's easy. It's if this is r equals sine 2 theta, maybe I write it upstairs. R equals to sine 2 theta is one of the graph that we did earlier. It looks like this. It looks like that. Okay, but what happened if I square it? What happened if I square it? I think it looks like this. Okay, well, anyway, how do we find out? Then, well, we did this problem earlier, right? Yeah, we did this problem earlier. So this will be, you will get theta equals to 0 and theta equals to pi over 2, right? Now then, how about our integral? Then the area of one loop will be 1/2 integral from 0 to pi over 2, okay, of r squared, But our r squared is already sine 2 theta. You see what I mean? Okay, and I think we can just integrate it directly from there, or let me see, sine 2 theta looks like this. This is pi. This is pi over 2. The answer is 2. So this is equals to 1. Is it equals to 1? I don't know. Put a question mark. Let's do it actually. So this is negative 1/2 cosine 2 theta from 0 to pi over 2. That's negative 1/4. And then that's negative 1 minus 1. Oh, sorry. That should be positive 1/2, not 1. Oh yeah, 1. The area here is 1. The area here is 1. The area here is 1. But I forget the 1/2 in front of that. Okay, 1/2 times 1. Okay, now we get it. Okay, now, but just for fun, let's take a look what it actually looks like. R squared equals to sine 2 theta. The radius is still 1, as I know. The radius is still 1. The distance from origin to the furthest point is 1. Okay, still 1 there. Okay, now what happens if I make it instead 4 theta here? Then it becomes 4 leaves. That's because of r squared, though, not because of r. If there's no square here, do you remember how many leaves we have? If there were no square here. Yeah, that's right. There will be 8 leaves. Okay, so that's for our finding the area. One more last question. The area between two curves. Let's say, for example, I pick question. This one is actually hard one though. Let's say, for example, I pick question number 26. Find the area of the region that lies inside the first curve and outside the second curve. Inside r equals to 2 plus sine theta, and outside of r equals to 3 sine theta. That's number 26. Let's sketch the graph. 2 plus sine theta. I wonder if you remember how to do that. Okay, so it will be symmetric with respect to the y-axis. 2 here, there will be 3 here, right? When theta equals to 0, the r is 2. When theta is pi over 2, that's the maximum 3. When the theta is 3 pi over 2 or negative pi over 2, that will reach the minimum 1. So the graph will be approximately like this. And then I copy paste the symmetry. Like this. Okay, and then outside of r equals to 3 sine theta. Now, if you remember, this is the circle with radius. This is the circle with radius 3 pi over 2, centered at 0.3 halves. So it looks like this. Okay, it looks like this. Now the question is, what is the area in between? Inside of the cardioid, but outside of the circle. I think I will just do one part and then I double it later on. Okay, so the area will be 2 times 1/2 of the area of the cardioid. Okay, that's from negative pi over 2 to pi over 2 of 2 plus sine theta squared d theta minus the area of the half circle. But that's actually pi times 3 over 2 squared. Okay, now actually I don't want to do it that way. Let me do it right. So minus integral from, I already factored the 1/2 out, from 0 to pi over 2. Okay, because for us to move from this point to that point, we just need from 0 to pi over 2 of 3 sine theta d squared d theta. Okay, that's what you need to do. Last one, how about on this topic, how about number 32? Find the area of the region that lies inside both curves. Inside r equals to 3 plus 2 cosine theta plus, and r equals to 3 plus 2 sine theta. Both cardioid. But one of them is on the x-axis, 5, 3, negative 3, 1, so 3. while the 3 plus 2 sine theta will be here, 5 here, 3 here, 1 here. Ooh, that's scary, huh? So we need to see where they intersect, actually. Okay, so actually, I don't think this is hard though. I don't think this is hard. Let's see where they intersect. Okay, where they intersect. The r should be equals when they intersect. So 3 plus 2 cosine theta equals to 3 plus 2 sine theta. Blah, blah, blah. We get cosine theta equals to sine theta. Now that only happens when theta equals to pi over 4 and or theta equals to 5 pi over 4. Okay, now so from theta equals to pi over 4, when theta equals to pi over 4, this is the angle here. This is pi over 4, while this is the other one, 5 pi over 4. Notice that the area in between both, basically the area here, multiplied by 2. Why? Because the area on the other side is actually congruent. Okay. So if I use the yellow one, the area equals to 2 times 1/2 integral from pi over 4 to 5 pi over 4. The red one is cosine. So 3 plus 2 cosine theta squared d theta. Now you work it out. Okay. That's for the area. Now, of all these things that we have done, it actually boils down to one important situation, one important question: how to find intersection of two curves in polar. Well, when two curves intersect, then at this point of intersection, they must share same r and same theta. Okay. There's actually another one case, or this one is harder to explain, or opposite r and theta differs by pi. Okay? That's another way. Now you will see that case later on. Let's say, for example, we do number 38. How do we find the intersection of r equals to 1 minus cosine? The best way is actually still graphing them. Okay, the best way is still take a look on the graph. So for example, we have this case number 38. They should have the same radius, 1 minus cosine theta equals to 1 plus sine theta. So negative cosine theta equals to sine theta. That's only true if tangent theta equals to -1. But tangent theta equals to -1 when theta is 3 pi over 4, or theta is 7 pi over 4. Okay. Now, how do we know that's the only answers we have? Then we sketch the graph. 1 minus cosine will look like this. This is 1 minus cosine. And 1 plus cosine will be like this. Notice that it has only 2 intersections, right? Of course, they have intersection at the origin also, okay? But at the origin, as long as the r equals to say 0, whatever the theta, it will be at origin. Okay. Now let me go on to the second part. Let me go on to the second part of this section is arc length. Now from long time ago, we have already learned the arc length. The arc length is equal to integral from a to b square root of dx squared dy squared. Now we will do the following derivative. It's very similar to what we have in the past when we did parametric. I will do the derivative of x respect to theta squared plus derivative of y respect to theta squared d theta. I just need to fix two things. What is dx d theta? Well, we know x is r as a function of theta cosine theta. Y as a function is r sine theta. So dr d theta will be, I need to do product rule. There will be I'm sorry, dx d theta, not dr d theta. Dx d theta will be dr d theta cosine theta minus r sine theta, while dy d theta will be dr d theta sine theta plus r cosine theta. My main focus is I need to generate this. I need to generate this, at least the radicand. So what is dx d theta squared? That will be dr d theta squared cosine squared theta minus 2r sine theta dr d theta plus r squared sine squared theta. Yeah, try to foil this. You can try to foil this. Okay, if you try to foil that, you will get what I have below. And then dy d theta squared will be dr d theta squared sine squared theta. Oh, actually I'm missing something above. 2r sine theta cosine theta. Okay, and then the one here will be 2r plus 2r sine theta cosine theta dr d theta plus r squared cosine squared theta. which if I add dx d theta squared plus dy d theta squared, notice that the first term add up to what?
To 1.
1 times dr d
dr
theta
squared.
squared, right? And then this term here will be zero, right? And then the last terms, when we add them, that will be plus r squared. So if I continue from this formula, there will be integral from theta equals to alpha to theta equals to beta of square root of r squared plus dr d theta squared d theta. That will be the formula. Then let's say, for example, number 48. We have r equals to 2 times 1 plus cosine theta. It looks like this. It's on cosine. So that's actually 4 here, 2 here, 0 here. It's a cardioid. That's what it looks like. Okay. Now suppose we want to find what's the circumference of this cardioid. What's the circumference of this cardioid? I will use symmetry. I will get the length from theta equals to 0 to theta equals to pi. Okay. And then later on, I will multiply by 2. Okay, so the perimeter equals to 2 times integral from 0 to pi square root of r squared plus dr d theta being squared, which will be 2 times, I'm sorry, it should be 2 times negative 2 times sine theta being squared d theta. Okay, it has common factor 2. So I will pull that 2 out. That will be 1 plus 2 cosine theta plus cosine squared theta plus sine squared theta d theta.
Wouldn't the first term be, isn't it dr d theta squared and not just r squared? For the
I swept
okay,
it.
okay. Sorry,
Yeah, I swept it. Yeah, that's okay. That's okay. Yeah. And then this will be 2, actually 4 now. Integral from 0 to pi of square root of 2 plus 2 cosine theta d theta. Now you may wonder, Thomas, now what? How to integrate this? What you can do, you use double angle formula. So we see, let me use another color. We see this cosine theta as cosine of 2 times theta over 2. I hope that helps. Okay, which will be 1 plus cosine squared of theta over, oh, I'm sorry, no, that's not it. That will be 2 cosine squared theta over 2 minus 1. You see what I mean? Okay, so then the integral now becomes, maybe I play around with that first. So 2 cosine theta will be 4 cosine squared of theta over 2 minus 2. Now 2 plus 2 cosine theta will be 2 plus that ugly guy, which is 4 cosine theta over 2. Okay, such that under square root, it becomes integral from 0 to pi of 4. Oh, no, not 4, like that. Becomes 2. Becomes 2 absolute of cosine theta over 2. I just try to be a bit careful that who knows my domain will include something that makes the cosine negative. Okay, well, because originally square root of x squared, keep in mind, square root of x squared is not equals to x. That's not true. It's only true when x is positive. Okay, that's only true when x is positive. It's supposedly square root of x squared equals to absolute of x. That's the correct one. Okay, so that's what I did there. Now then from there I see, oh, you know what? My domain of integration makes my angle here always positive anyway. Cosine theta over 2 always positive in quadrant 1 and quadrant 2. Right? Okay, so it will be 0 to pi of cosine theta over 2 d theta. That will be 8 times 2 sine theta over 2 from 0 to pi. That's 60. Okay, so the length here, the yellow one, you will see the length is 8. And then the length for the blue one is another 8. That's why the total perimeter is 16. Okay. I think that's where I want to stop for this section. Only one example, I think that's good enough. You just need to do a lot of exercise here. Then your suggested homework from this 10.4 will be number 1 to number 1 to number 11, and then number 17 to number 41. 17 to 41, and then 45, 47. That should be good enough. Right now it's 5:38. Let's take a break. We come back at 5:50. Even though it seems like I'm rushing through this 10.4, but you will see basically what you need is what you need are, first you need to know how to graph a curve, okay? And how to apply the formula, find the angle where the limit of for the limit of integrations, okay, and what else? And when we comes to sketching, I mean finding the arc length, you need to know how to simplify the guy inside. Well, you will need to memorize this formula here. You will need to memorize the formula here. Okay, you need to memorize that, but somewhere in between, when you simplify this expression here, you need to be a bit careful. Okay, you need to be a bit careful. But other than that, if your algebra is good, you should be fine. Now, how to know see common mistakes? Do more exercise. Okay, do more exercise. Now let me go on to 11.1. That's chapter 11 on sequence and series. Now, this section, we will learn about sequence. Sequences. Now, what is a sequence? A sequence is a list of numbers. A list of numbers in certain order, in a definite order. That's the word our textbook use. Now, a sequence usually denoted by, maybe I write it down, a sequence is usually denoted by first one, listing method, by listing A1, A2, A3, and on, okay, where AI is the ith term, let's say, for example, if I do this list, the list of 5, 8, 11, 14, and on. Now then, the first term of this sequence is 5. The second term of this sequence is 8. The third term of this sequence is 11, and so on and so forth. Okay, basically we listed from the first term and on. Now this method is usually being used, especially if we don't see the pattern of the sequence. The second method is by using general formula. General formula or general term, where the a sub n as a function of positive integer, or let me just call that integer n. Let's say, for example, a sub n is equals to 3n plus 2. Now, 3n plus 2 for n greater or equals to 1. By the way, if we use general term, it is a custom to have the n start from 1 unless otherwise mentioned. Okay? Unless they say, well, the n start from 0, or the n start from 2, or the n start from 3. If they don't say the n starts from what number, then we will start from 1. Okay? Now that's the general term. By the way, if you want to find out, if I give you a general term like this, and you want to find, oh, what is the first term? The first term, basically you plug in n equals to 1. The second term, you replace the n by 2. And so on and so forth. Okay, so from the general term, we will be able to find the listing. Okay, from the general term, we will be able to find the listing. But from the listing, we may not always get the general term. Now, the third method, which is being used a lot in computer science, is recursive formula. Recursive form or recursive formula, where the current term depends on is a function of previous term. Let's say, for example, a sub n, the current term is the previous term plus 3. Yeah, but if I use recursive form like that, I need to inform you what is the value of the first term. So for example, I say the first term here is 5. Okay, so what is the second term? The second term is the first term plus 3, which is 5 plus 3, which is 8. The third term is the second term plus 3, which is 8 plus 3, that's 11. So on and so forth. Okay, so what we mean by recursive form is this one here. That's the recursive form. This is the general term. Okay, and this is just the listing. So we write the sequence explicitly. Okay, now with that said, let me ask you to do a little problem from page 724. From page 724, I would like you to do number 4. A sub n equals to 3 to the n over 1 plus 2 to the n. List the first 5 terms of the sequence. List the first 5 terms. That's for number 4. And then number 8. A sub n equals to negative 1 to the n of n over n factorial plus 1. And then number 10, a1 equals to 6, an equals to an plus 1 equals to a sub n over n. Okay. Let me give you 1, 2, 3, 4, 5, 6, approximately 6 minutes from now. For this number 8, notice that the sign alternates positive, negative, positive, negative, positive like that, or in this case, it's actually from negative to positive, negative, positive, negative. Okay, now you will see that this guy here is later on called alternator. Okay, it makes the terms becomes plus minus, plus minus, plus minus. And this sequence is called alternating sequence. Okay, that's for number 8. Number 10, I already have A1, then A2 will be the previous term over 2, that's 3. A3 is the previous term over 3, 1. The fourth term is the previous term over 4. The fifth term is the previous term over 5. That's 1 over 20. Okay, so we usually write the first 5 terms, therefore, in the in order. Instead of writing them like that, we're supposed to write it this way: 1, 9 over 5, 3, 81 over 17, 81 over 11. Okay, and then for this guy here, negative 1/2, 2/3, negative 3/7, 4 over 25, negative 5 over 121. And the last one, 3, 1, I'm sorry, it's supposed to be from 6, 3, 1, 1, 4, 120. Okay.
Professor, I don't understand number 10.
Number 10, the first term is 3. I mean, the first term is 6.
Okay, so A1 is 6, and then how did we determine A2?
A2 is A1 plus 1. Right? You see from here? Which means, according to the formula, that's A1 over... Oh, I'm sorry. My bad. You are right, you're right. I used the wrong formula. It should be A1 over 1. Thank you. So, sorry. So this should be over 1 here. I think the rest are actually all wrong. Because it's recursive. Once one of them is incorrect, then the rest will be incorrect also. Yeah, thank you for asking though. Otherwise, I won't realize that this is 6. A3 will be A2 plus 1 over 2. Right? The previous term divided by 2, that's 3. A4 is the previous term. Is the previous term. So that's A2 over 2. This is A3 over 3. Okay, so A4 will be A3 over 3. That's 1. And A5 will be the previous term over 4, huh? So that will be 6, 6, 3, 1, 1, 4. Okay, because the fifth term is the fourth term. The fifth term is the fourth term divided by 4. Why doesn't it work? The fourth term divided by 4. Okay, that's how I get that. That's for number 10. Now, the following is instinct. Okay, now A sub n can be seen as Fn, okay? Or kind of like think of that as Fx with integer domain. So for example, if I have a sub n, the general term is 3n plus 2, you can think of that as Fn equals to 3n plus 2. You can think of it that way, okay? Or to go even further, you can kind of like imagine even further, this is Fx equals to 3x plus 2, okay? But the x has to be a positive integer. Okay, such that if later on we sketch the graph, if I sketch the graph, when I sketch the graph, it will be following that 3x plus 2, okay? This is just a sketch, 3x plus 2, but I take the domain is instead of the domain all real numbers, I only take the domain 1, 2, 3, and on. Okay, so this is my A sub 1, this is my A sub 2, this is my A sub 3, and on. This is my 1, 2, 3. You see what I mean? Fx will give us the quote-unquote continuous function, maybe, not always. Okay, in fact, in general, that's not the case. Okay, yeah, that gives us the smooth curve, while the sequence is actually something looks like this. Okay, that's what it looks like. Now, it happens that the underlying function, I call it superposition function, it turns out that this function here is continuous, but it doesn't have to. It doesn't have to. Okay, it doesn't have to. Now, what is the purpose of this section? This section is not, the purpose of this section is not to find the terms. That's too easy for calculus 2 students. Okay, the main purpose of this section, is to analyze if an converges. Okay, if the sequence converges. Basically, if A sub n converges to, let's say, value L, what does it mean? Then that's basically limit n goes to infinity of A sub n equals to L. Okay, that's what it means to say that A sub n converges to L. Now, to be more precise, using the idea of limit we have from calculus 1, that's equivalent to say, that's the same to say that the distance from the nth term to L will be less than epsilon as long as, or whenever, n is greater equals to capital N for some n. Thomas, I don't really get it. Think of that as, think of this as the horizontal asymptote, quote unquote, horizontal asymptote on the far right. As n goes to infinity, when n goes to infinity, what's the value of the sequence? Does it converges to a certain number? Okay, now because it is defined using the condition of limit, then the way we do this mostly will be in terms of limit. Let's say, for example, number 24. Number 24, the question is, determine whether the sequence converges or diverges. If it converges, find the limit. So a sub n equals to n cubed over n cubed plus 1. Does this sequence converges? If it converges, find the limit. So what we will do is we need to find the limit n goes to infinity of that sequence. The way we do this problem, we need to follow the idea of limit that we learned in calculus 1 and also calculus 2, that because we did some limit before. Okay, now here's the thing though. This sequence here, it is a sequence. It is a sequence, which means the function is not continuous. Take a look. If this is fx, then it is the blue line. It is continuous, okay? But we are not dealing with the blue line. We are dealing with the red dots. We are dealing with the red dots. Now, why I need to mention it? Then, because this sequence is not continuous, okay? Because the domain only integers, right? Then, because it's not continuous, we cannot apply L'Hopital rule. Let me say it again. Let me say it again. A sequence is not a continuous function. So one of the consequences is, so can't use L'Hopital rule directly. Okay. In this question, we actually don't need to use L'Hopital rule. We can just use the method that we learned before. For example, I divide by n cubed on the top and the bottom. So divide by n cubed on the top. You need to show me that though. Okay, divide by n cubed at the bottom. That's limit n goes to infinity of 1 over 1 plus 1 over n cubed. Now, when I substitute the n by infinity, I get 1 over 1 plus 0. That's equals to 1. Is it okay? Now, that's the first method to do it, and that's the method I like. That's the first method. Now, the second method, relies on a theorem that we use in the book. So please put this as one method to find the limit of sequence. This usually called method of continuous superposition function. Our textbook explained this method, even though was not were not explicitly mentioned the name. In fact, most textbooks don't mention the name. I remember my professor used this term though, and that's how I learned this terminology. Basically, the idea is this. Note that we can write our nth term as fn, right? Okay, and fn is a subset of fx. Thomas, I don't get it. I don't get it. I don't get it. Okay, think of it this way. Think of it this way. Suppose I have a rectangular coordinate system. I don't need a big one. Sorry. And then I have the sequence when I graph them turns out to be like this. Okay, those are the terms. Okay. Now, when I say these terms, a sub n is a subset of fx, it is actually that this red dots is part of this curve. This red dots actually part of this curve.
So the dots are Fn and the whole curve is f of x?
That's correct. Mm-hmm. Yes. Now notice if fx converges to L as x goes to infinity, then Fn must also converges to L as n goes to infinity. Do you notice that? If this blue line here, converges to a certain number, if it has horizontal asymptote, then the sequence, which is part of this curve, the dots, which is part of this curve, must also converge to the same value, same to the horizontal asymptote. Does it make sense? Okay. So using this idea, we can solve that problem. Using this idea, we can solve this problem. We say let fx equals to x cubed over x cubed plus 1. Okay. Note that fn equals to a sub n. If I change the x, which is a real number, into n, when I change the x into n, then I get the sequence. Okay? Now then, let's see what happened to the limit of this, continuous function. Limit x goes to infinity of fx will be limit x goes to infinity of x cubed over x cubed plus 1. Okay, now then from here you can divide by x cubed. That's the first method. You say limit x goes to infinity of, oops, x cubed over x cubed big over x cubed over x cubed plus 1 over x cubed blah blah blah, which is basically the way we did it in the first method. Okay, but the reason I show you this, because once you have a continuous function, then you can apply L'Hopital rule. This is when you can apply L'Hopital rule. You cannot apply the L'Hopital rule directly from the function, from the sequence. Okay, you can only apply the L'Hopital rule once you have a continuous function. Okay, now then if you apply a continuous function, L'Hopital rule, you will get limit x goes to infinity of 3x squared over 3x squared, right? You can apply L'Hopital rule again if you want to, but I don't think that's necessary, because what happened is we get limit x goes to infinity of 1, which is 1. I believe that's what we get earlier. Okay, my point in this number 24 is, if you insist to use L'Hopital rule, you need to first find a continuous function. You need to first find a continuous function whose fn equals to the sequence. Okay, whose fn equals to the sequence. So you can do it this way. Now, with some extra note, another extra note, if the limit x goes to infinity of fx diverges, does not imply that a sub n is diverges. No. Okay, the converse is actually not true. What I said was limit x going to infinity. If fx convergent, then the subset must be convergent. Okay, but if the function diverges, it doesn't mean the subset is diverges. No, it's not true. Okay, in fact, I can give you one example right away. For example, consider this sequence here, the sine and pi. What is a sub 1? A sub 1 is 0. A sub 2 is 0. A sub 3 is 0, and so on. So this sequence is actually 0, 0, 0. The first term, second term, all terms are all 0, right? So you can see directly that sine and pi is actually converges to 0 as n goes to infinity, right? Now, however, if you use the method of continuous superposition, let's say you say let fx equals to sine pi x. Okay, notice that this function is not convergent. Okay, it will be fluctuating between -1 to 1. So sine pi x has no horizontal asymptote. Okay, sine pi x has no horizontal asymptote. Now we can see it this way actually. Suppose this is my coordinate system, and I deal with sine pi x. Sine pi x looks like this. Okay, that's what sine pi x look like. Now, however, sine n pi only this guy and this guy and this guy. Okay, even though the continuous superposition function is fluctuating, it's actually periodical between -1 to 1, but right at n pi, when x is integer, sine n pi is 0. Okay, so be careful with that. Be careful with that. That we can use this superposition method only if it is divergent. I mean, only if it is convergent. If it is divergent, we can't really tell. We need to be more careful. Okay, we need to be more careful. Of course, if the limit goes to infinity, or if the limit goes to infinity or negative infinity, then we can safely say that the sequence also convergent to positive or negative infinity. Okay. Yeah, but if we find out to be not exist, then it doesn't mean the sequence diverges. No, we need to use another method. Okay. Let's see, for example, number 28. Number 28, the nth term is, the nth sequence is 3 to the n plus 2 over 5 to the n. Find the limit. Limit n goes to infinity of 3 to the n plus 2 over 5 to the n. Now, do not rush to L'Hopital rule. Don't rush to L'Hopital rule. Trust me, it's more about your algebra here. I will rewrite that 3 to the n plus 2 as 3 squared times 3 to the n over 5 to the n, which will be limit n goes to infinity of 9 times 3 over 5 to the n. Now then, this is 9 times limit n goes to infinity of 3/5 to the n. Notice that the base is between 0 to 1, right? Okay, so if you kind of like imagine the graph here, just for this part, then it will be exponential function, right? Decreasing because the base is positive but less than 1, right? And the sequence will be here, right? You see what I mean? So what's the limit? The limit of this one,
Is it equal to 0?
equals to 0. Okay, that's for number 28. There's one theorem in our textbook. I don't think they prove it, but they have the following. Actually, two theorems to mention, and we will use this very soon. The first one is let f(x) be a continuous function and then a sub n converges to L, in continuous function be continuous at, sorry, the f(x) be continuous, sorry, continuous at x equal to L, and a sub n converges to L, then limit n goes to infinity of f a sub n is equals to FL. Thomas, I don't know what's that. That's confusing. Don't worry, don't worry. Let's see a simple example. Suppose I have sine 1 over n. Okay, now this a sub n will converge to what? The way we see is the following. Now 1 over n converges to what? One over n converges to 0, right? And sine x is continuous at x equals to 0. Is that right? Now, so sine 1 over n will be convergent to sine 0, which is 0. Okay, notice what I'm doing is this. What I'm doing is this. Sine is a continuous function. Okay, so if I know the limit of this is 0, then the limit of the whole thing here will be sine 0. Okay, that's one. Another good theorem to know is if a sub n, absolute of a sub n converges to 0, then a sub n converges to 0. Only for 0, only for 0, not for other number, not for other number, only for 0. The proof this here relies on, the proof here relies on squeeze theorem. Okay, now because we use squeeze theorem, then it should go down to 0. Okay, let's use this. For example, we do problems that seems to be quite difficult, but knowing those theorem, it becomes quite easy. For example, number 32. The sequence of e to the 2n over n plus 2. Yeah, notice that when we try to find the limit here, limit of n goes to infinity of e to the 2n over n plus 2, that's actually the same to e to the limit of n goes to infinity of 2n over n plus 2. You see what I mean? Because e to the x is a continuous function, right? So then this is equals to e to the limit n goes to infinity of divided by n on the top terms, divided by n at the bottom terms. Okay, or a better way to look at that is the following. You will do limit n goes to infinity of 2n over n plus 2 first. You get that's equals to 2, right? So limit of n goes to infinity of e to the 2n over n plus 2, this will be e to the 2. Okay? But you need to show this first. You need to show this first. Another one. Let's say, how about, how about number 36? I think that's very, very simple. Number 36, we have the nth term equals to, cosine of 2 over n. Now then the way we argue, since limit n goes to infinity of 2 over n equals what? Equals to 0. And cosine x is continuous at x equals to that 0. Then limit n goes to infinity of cosine 2 over n is equals to cosine 0, which is 1. That's how we argue about it. Okay. Now, how about number 46? Number 46, the nth term equals to 2 to the power of negative n cosine n pi. Now notice that this part here, will give us alternating value. Right? So if we kind of like look at this sequence here, you will get negative 2 to the power of negative 1, positive 2 to the power of negative 2, negative 2 to the power of negative 3, and on. Okay, actually it doesn't have to be alternating though. It doesn't have to be totally perfectly alternating like this. Now, what I want to show you is how to use how to use this one here, how to use this one here. Okay, that's what I want you to see. Notice that consider absolute of a sub n. Which is absolute of 2 to the negative n cosine n pi. Right? But that's equals to absolute of 2 to the negative n times absolute of cosine n pi. Is it right? Now, 2 to the negative n is always positive. So I can take the absolute sign off, while this guy here, the inside is either a -1 or 1, such that with absolute, it will always be 1. Right? So then we say limit n goes to infinity of absolute of a sub n equals to limit n goes to infinity of 2 to the negative n. What is that equal to? If you cannot see it well, you can do it this way. Rewrite it, make it in the way that you can see better. This is equals to 0. Right? Okay. Now, so limit n goes to infinity of a sub n, which is 2 to the negative n cosine n pi, will also be equals to 0. Okay, maybe I write it this way. Now notice that this technique of squeezing it to 0 also applies to number 48. At sine 2n over 1 plus square root of n. Note that absolute of 2n, okay, is less than equals to, maybe I write it this way. Give me a second. I need to be patient. Equals to absolute of sine 2n over 1 plus square root of n. Is it right? But sine 2n may be positive, may be negative. Okay, the value between -1 to 1. But once you put it in absolute sign, then it will be at most 1. Right? Okay, so limit n goes to infinity of absolute a sub n is less than equal to limit n goes to infinity of 1 over 1 plus square root of n, which is equal to 0. Notice that this guy here is always greater or equals to 0. Okay, by squeeze theorem, therefore, limit n goes to infinity of absolute of sine 2n over 1 plus radical n is 0. Therefore, limit n goes to infinity of the one without absolute sign will also be equals to 0. Okay, why does it have to be equals to 0? What happens if the limit is not equals to 0? Consider the following. Let me use red color. Note. Suppose limit n goes to infinity of absolute a sub n is L, which is not 0. Now, it does not imply that limit n goes to infinity of a sub n equals to L. Now, pay attention to the following example. A sub n equals to cosine, no, actually, yeah, cosine n pi. If you think about this sequence, cosine n pi is -1, 1, -1, 1, -1, and on, right? This is not convergent. It doesn't converge to 1, it doesn't converge to -1, okay? However, when you look at the absolute sign, the absolute of that, you will see that it's convergent to 1. Right? So it is possible the sequence is actually alternating. Okay, it's the sequence is alternating plus minus 1. When you apply absolute, it gives you 1. Okay, so the only time this will work is when the limit of the absolute actually goes to 0. Okay. What else? Let's see, the last one is I kind of like get to sink into this discussion here. How about number 52? We have the n term equals to n minus square root of n plus 1 times square root of n plus 3. I don't even know what's the limit. Let me just write it down first. Limit n goes to infinity of n minus square root of n plus 1 square root of n plus 3. The thing is, if I apply infinity right away, I will get infinity minus infinity. That's not good. Then what should I do? Let me try multiplying by the conjugate. Who knows it works? N plus square root of n squared plus 4n plus 3 over n plus square root of n squared plus 4n plus 3. That will give me limit n goes to infinity of, on the numerator I get n squared minus n squared plus 4n plus 3 big over n plus square root of n squared plus 4n plus 3. That is equal to limit n goes to infinity of -4n minus 3 on the top, and at the bottom I have n plus square root of n squared plus 4n plus 3. Uh-oh, I still don't know what to do here. I cannot just plug in infinity though. I get infinity over infinity later on, or negative. What I think I will do is I will divide the top and the bottom by n. If I divide the top and the bottom by n, so you show the detail yourself, and I get limit n goes to infinity of what happened on the top. -4 minus 3 over n. 1 plus square root of 1 plus 4 over n plus 3 over n squared. Then that will give me -4 over 1 plus 1. That's -2. Okay. I'm not done with this section yet. I have one big theorem that I have not covered. I will cover that later on. And there actually are plenty of things we can do here, though. Yeah, there are plenty of things we can do in this. Still, plenty of things we can do in this section. But for now, let me ask you to do suggested homework 11.1, number 3 to number 53. Okay, let's call it 11.1a. On Wednesday, I will continue on this 11.1. Just a bit more, maybe another half an hour. Yeah, maybe just another half an hour. And then I go on with 11.2. Okay, then see you on Wednesday.
Thank you, Professor. See you Wednesday.